The Big Bang Theory and the Evolution of Cosmology. The Big Bang Theory has impacted our comprehension of the cosmos, establishing the foundation for present-day cosmology. Based on Einstein's theories and accepted as traditional cosmology, the cosmic era following the Big Bang begins with the expansion, the source of all matter, energy, and space, around 13.8 billion years ago. This occurrence resulted in the vast universe we now perceive. But recent developments in cosmology suggest it's possible that the Big Bang was not the ultimate origin. There may have existed events prior to the Big Bang, which were equally crucial in the formation of the cosmos as it currently appears to us. One such concept is known as the epoch of cosmic inflation. According to contemporary cosmology, prior to the intense heat of the Big Bang, the universe went through an exceptionally quick, exponential expansion. During this time, the universe's size grew at a remarkable speed. To demonstrate how rapid this growth was, if the universe contained less mass, it would have begun smaller than an atom, and within a fraction of a second, expanded to a size larger than the entire observable universe. This brief period of rapid inflation was essential to forming the cosmos. When the power of expansion was cut off by inflation, energy was launched into space, heating it and causing particles to form, particles that include everything we now observe. In many models, inflation is seen as the predecessor to the Big Bang itself. Despite the prominence of the Big Bang, the inflation hypothesis is well acknowledged. Yet, many unanswered questions in cosmology remain unresolved. For example, we have yet to identify the factors that contributed to inflation, how long it lasted, or what caused it to stop. These are some of the most intriguing mysteries in cosmology, and their resolution is essential for a more thorough comprehension of the beginnings of the universe. Before inflation, the cosmos was an extremely dense, minuscule point frequently referred to as a singularity. The subsequent expansion ultimately led to the creation of atoms, stars, galaxies, and molecules. While the idea that the Big Bang marked the beginning of everything is attractive, modern cosmology suggests a more complex picture. Theories suggest that the universe encountered a period prior to inflation. Following the Big Bang, the universe grew exponentially, increasing in size by a factor of at least 80 times. This rapid expansion was driven by an unknown source of energy dispersed throughout empty space. That energy, which remained after inflation ended, transformed into particles, heating the cosmos. This led to the hot, dense condition we now refer to as the Big Bang. Despite being cold and empty, the inflationary stage established the foundation for the universe and everything we now see. One of the most speculative and fascinating ideas in modern cosmology is the theory of eternal inflation. The idea that inflation continued constantly everywhere, creating numerous diverse regions or bubbles, each potentially existing as a separate universe. In accordance with this idea, our universe would be just one of these regions. There could be an infinite number of these worlds, each with its own distinct set of physical constants and laws. This leads to the concept of the multiverse. Our world might be merely one in a vast, or possibly endless, supply of universes. If this hypothesis is correct, it may help explain why the conditions in our universe are so just right for life. In this multiverse model, physical laws could vary from universe to universe. We simply happen to live in a region where the conditions allow for the formation of stars, and elements like carbon and oxygen, essential for life, to appear. Despite ideas like the multiverse and eternal inflation, the idea of inflation itself is well supported by empirical evidence. The most compelling comes from the cosmic microwave background, CMB, the oldest light in the universe, released 380,000 years after the Big Bang, once the universe had cooled enough for atoms to form. This moment marked the time when the cosmos became transparent. The light has been traveling through space ever since. Studying the CMB allows cosmologists to essentially capture a baby picture of the universe. One of the most important discoveries came from the European Planck spacecraft, which took high-resolution photographs of the CMB. These images revealed tiny variations in temperature, consistent with predictions made by inflationary theory. This experimental validation supports the notion that inflation is not just speculative, it's a fundamental aspect of our understanding of cosmic origins. Understanding the Big Bang and its aftermath requires merging two of the most crucial ideas in modern physics, Einstein's general relativity and quantum mechanics. General relativity explains the large-scale structure of the universe, including the behavior of stars, galaxies, and gravity. Quantum theory, conversely, explains the behavior of the smallest particles at the tiniest scales. To fully answer cosmological questions, such as what space and time truly are, or what existed when the universe began, scientists are working to create a unified theory that combines these two frameworks. Such a theory might help us understand not only the Big Bang, but also what led to it. A surprising fact about the universe is that the largest visible structures are about 47 billion light-years away, meaning the observable universe is roughly 94 billion light-years across. This may seem contradictory since the universe is only 13.8 billion years old. The solution lies in the fact that the universe has been expanding. As it grows, distances between objects increase faster than light can travel. Most scientists believe the universe is much larger than we can observe, and perhaps even infinite. The observable universe is just the part we can see, limited by how far light has traveled since the beginning of time. There may be regions of the cosmos that we will never be able to access. Despite this, the concept of a boundary to the universe may not make sense. Space and time themselves are properties of the universe. Asking what lies outside the universe may be as meaningless as asking, what's north of the North Pole? These questions, though difficult, are essential. They push the limits of human understanding. Theoretical physics continues to develop new ideas to address these puzzles. One such idea is string theory, which proposes that the fundamental components of the universe are not particles, but tiny vibrating strings of energy. This theory also introduces additional dimensions beyond the three we know, dimensions so small they are undetectable with current technology. Another emerging theory is loop quantum gravity, which attempts to combine quantum mechanics and general relativity. According to this theory, space itself is quantized, made up of tiny discrete units, like pixels on a screen. This perspective suggests the Big Bang may not have been the true beginning, but rather a bounce from a previous collapsing universe. These new models challenge traditional Big Bang narratives and offer alternative views of the cosmos's origin and structure, though they remain speculative and lack comprehensive empirical evidence. Still, they represent the forefront of contemporary cosmology. Meanwhile, observational tools are advancing. The James Webb Space Telescope, JWST, for example. Great deal about the universe, from its fiery birth in the Big Bang to the cold, distant future of a potential heat death, many questions remain unanswered. Our understanding continues to evolve as new theories emerge, observations deepen, and technologies improve. The journey of cosmology is not merely about distant galaxies or abstract physics, it's about unraveling the very origin and fate of everything that exists, including ourselves. Some scientists have proposed alternative endings beyond heat death. The Big Rip hypothesis suggests that if dark energy's repulsive force continues to grow stronger, it could eventually overcome all forms of matter and gravity. In this scenario, galaxies, stars, planets, atoms, even spacetime itself, could be torn apart. On the other hand, there's also the Big Crunch theory, where the universe, after expanding, might reverse into a collapse, potentially initiating another cycle, a cosmic rebirth. Yet, all these possibilities depend on the exact nature and behavior of dark energy, which remains one of the greatest mysteries in physics. Is it a constant force? Does it evolve with time? Could it decay or reverse? Answering these questions is crucial for predicting the ultimate fate of the universe. Moreover, quantum theories challenge the very idea of a single universe. In quantum cosmology, some interpretations suggest that entire universes may spontaneously emerge from quantum fluctuations, giving rise to a multiverse not through inflation, but through quantum birth. In this view, our universe is one of countless bubbles, each possibly governed by different laws. Holographic principle is another radical idea suggesting that all the information in our universe might be encoded on a two-dimensional surface at the boundary, like a cosmic hologram. This challenges our very perception of dimensions and space, hinting that the universe is far stranger than we imagine. Despite all these advances and theories, we are still standing at the edge of understanding. Each discovery opens new doors, and each answer raises deeper questions. What is time? What caused inflation? Why do the laws of physics seem fine-tuned for life? Are we truly alone in the vast cosmic expanse? Cosmology continues to be a breathtaking endeavor, one that combines mathematical precision with boundless curiosity. As our instruments peer deeper into the ancient light of the cosmos and our theories stretch further into the fabric of reality, we are reminded that the universe is not just a subject of study, it's a mirror in which we search for meaning, origin, and destiny. A great deal has been learned about the origins of the universe through the inflationary theory and research into the cosmic microwave background. However, many questions remain unanswered regarding the cause of inflation, what initiated it, what prevented it, and whether anything exists outside the observable universe. How many alternative multiverses exist? As scientists, we continue to investigate the universe using advanced concepts and cutting-edge technologies. Quantum mechanics, along with general relativity, will undoubtedly help us learn more about these mysteries. Attempting to comprehend the universe is an ongoing process, and each new discovery brings us closer to answering the fundamental questions about our existence. Examining the universe's structure and beginnings is not only a scientific challenge but also raises real-world philosophical questions about existence and our role in it. One of the main topics in cosmology is recognizing dark matter, which is believed to account for approximately 27% of the mass and energy in the universe. Dark matter is unlike regular matter. It does not produce, reflect, or absorb light, making it undetectable by traditional means and only observable through its gravitational effects on visible matter. Understanding dark matter is essential to comprehending the formation and current dynamics of galaxies. Experiments and observations have provided insight into its possible characteristics, although specific details remain unknown. Candidates have been proposed, including weakly interacting massive particles, WIMPs, and actions, but no concrete evidence has confirmed the existence of dark matter particles. The search continues through a combination of astronomical observations and ground-based simulations that analyze how cosmic structures are influenced by dark matter. Dark energy is another significant and mysterious force in cosmology. It is believed to be responsible for the accelerating expansion of the universe and constitutes about 68% of its total mass energy content. Its unexpected discovery has led to various theories, including the cosmological constant and dynamic models like quintessence. Understanding dark energy is critical, as it could determine the ultimate fate of the universe. Researchers are investigating whether dark energy remains constant over time or evolves and how it affects celestial structures. In addition to dark matter and dark energy, studying the development of cosmic structures provides valuable information about the universe. Measurements of cosmic filaments and galaxy clusters in the cosmic web demonstrate how matter clusters under gravity, resulting in the complex structures we see today. Supercomputer simulations are instrumental in understanding how these structures have formed and evolved over billions of years. At the intersection of cosmology and astrobiology, scientists aim to understand the conditions necessary for life beyond Earth. The search for extraterrestrial life outside our solar system has intensified in recent years, with thousands of exoplanets discovered, some of which lie in habitable zones where liquid water might exist. By studying these distant planetary systems, researchers hope to determine the potential for life in other parts of the universe. Physics also plays a crucial role in cosmology. The pursuit of a unified theory that merges general relativity with quantum mechanics remains a central challenge for physicists. Theories such as loop quantum gravity and string theory aim to bridge this gap and may eventually explain phenomena like the formation of the universe and black holes. Technological advancements have significantly enhanced our ability to observe and understand cosmic phenomena. Tools like the James Webb Space Telescope are revolutionizing our understanding of the cosmos, offering unprecedented data on distant galaxies and cosmic events. With each new observation, we continue to piece together the puzzle of the universe's creation, development, and ultimate fate. In summary, the study of the cosmos spans numerous scientific disciplines and intellectual pursuits. From exploring the factors that influence the appearance of cosmic structures to the search for alien life, humanity's quest for knowledge reflects our profound curiosity about the universe. Each insight not only answers old questions but deepens our appreciation for the vastness and complexity of existence. The connection between observation and theory in cosmology is vital. New technologies, such as advanced machine learning algorithms and sophisticated detectors, are improving our ability to analyze astronomical data. These tools help researchers sift through enormous datasets, identifying patterns that may reveal new perspectives on cosmological phenomena. A crucial area of study is gravitational waves, ripples in spacetime caused by cataclysmic events like black hole or neutron star collisions. The discovery of these waves has opened a new window into the cosmos, allowing scientists to test theories under extreme conditions and gain fresh insights into gravity. The concept of cosmic time is also fascinating. Unlike our everyday experience of time as uniform and linear, cosmic time is influenced by the universe's expansion, raising questions about whether time is absolute or relative to the observer's motion and location. These philosophical questions follow naturally from scientific exploration. Studying the formation of the first galaxies and stars, often referred to as the cosmic dawn, is another important area. Understanding this era helps explain how the universe evolved from a hot, dense state into the complex systems we observe today. High redshift galaxy observations provide crucial clues about the processes that occurred during this formative period, enabling scientists to establish a timeline for the universe's evolution. As we advance our understanding of the universe, interdisciplinary collaboration becomes increasingly vital. Cosmology, physics, astronomy, mathematics, and computer science are all deeply intertwined in the quest to unravel cosmic mysteries. Researchers rely not only on observational data but also on theoretical models and simulations that stretch the limits of current computing power. One particularly intriguing area of study is the potential existence of a multiverse, a collection of universes beyond our own, each possibly governed by different physical laws. While still speculative, this concept arises naturally from certain interpretations of quantum mechanics and inflationary cosmology. Though direct evidence remains elusive, the idea continues to inspire new theories and approaches to understanding our cosmic context. The role of entropy and the arrow of time also present philosophical and scientific challenges. Why does time appear to move in only one direction? How did the universe begin in such a low entropy state? These questions touch upon the very foundations of thermodynamics and cosmology, inviting deeper reflection on the nature of reality itself. Moreover, black holes remain among the most mysterious and captivating phenomena in the universe. They not only challenge our understanding of gravity and spacetime but also represent extreme environments where the known laws of physics break down. The study of event horizons, Hawking radiation, and singularities may eventually lead to breakthroughs in reconciling quantum mechanics with general relativity. Meanwhile, cosmic background radiation continues to offer valuable insights into the early universe. By studying its tiny fluctuations, scientists can infer information about the density, composition, and expansion of the universe shortly after the Big Bang. This radiation serves as a fossilized imprint of the universe's infancy, guiding cosmological theories and calibrating observational data. New missions and observatories are on the horizon, each promising to expand our understanding further. Projects like the Vera C. Rubin Observatory, the Euclid Space Telescope, and the Square Kilometre Array, SKA, are set to provide unprecedented views into deep space, enabling scientists to map dark matter, trace cosmic structure formation, and detect new gravitational wave events. Education and public outreach also play a crucial role in the advancement of cosmology. Inspiring the next generation of scientists requires making these complex ideas accessible and engaging. Popular science publications, documentaries, and interactive exhibits at planetariums and museums help bridge the gap between cutting-edge research and public curiosity. Ultimately, the study of the cosmos is not just about gaining knowledge, it's about placing humanity within a larger framework. Understanding where we came from, how the universe works, and what lies ahead gives context and meaning to our existence. In this ongoing journey, science and philosophy walk hand in hand, each enriching the other. As we continue to explore the vastness of space, our sense of wonder grows with each new discovery. The cosmos remains a boundless frontier, calling us to ask deeper questions, seek greater understanding, and embrace the beauty of the unknown.